look at first the not this the VPL, the virtual physics labs. So this one was, you would tell how well you did because you can look up the actual magnetic field at in the Bahamas or Bermuda, wherever they picked. And so the big idea here was that you don't have a direct way to measure the Earth's magnetic field, but you do have a way of setting up a known magnetic field, and you put it at 90 degrees. Let's see, I need a notes window. Yeah, this. So where should we put this? We'll put this at the top. New slide. And so the objectives for this lab were to uh, getting my tablet, my drawing tablet here. So we were so it was about what the B field basics, like north and south, right, and the north to south of the field lines. And let's see what else. The B fields around currents. And the thing to notice about magnetic fields is they tend to be sort of more circular oriented. Like if I have a wire, the B field goes around it. And so in this case, the current is out of the page. I is out of the page here. So if I put my thumb pointing out of the paper, the B field is counterclockwise. Uh, and that's one of the reasons you see a lot of cross products, QV cross B. This is also because B fields don't do work. So they can't cause B fields do no work, at least on charged particles. So that means that delta Ke is always equal to 0 when it comes to magnetic fields. Because in general, we don't talk about two magnets being attracted to each other and then speeding up or slowing down. You'll notice we don't really, there's no kind of problems like that. Or like you don't see a kind of problem like you have for charged particles, the Coulomb force. There's no sort of analog, there's no B field analog to this one. And in fact, remember too that we were introduced to I introduced you to this gradient operator, and so that's turning a scalar into a vector, and there for B fields. And so the volts, that's the scalar potential in general terms. And so E fields come from a scalar potential, and it turns out that there's an analogous equation for magnetic fields, and we have this vector potential. Although we don't get into that into that in 2000 level. So this one is called a gradient operator. And so that sort of tells you something about sort of like gravity. Sometimes they picture gravity like an Earth or a sun, and it brings this sort of cone shape down, and marbles fall into it to think of gravity. So a gradient, like the slope of a hill. Whereas when you take the same the nabla operator here, this is called. Then when you use the cross product, this is called a curl. And so B fields have to do with circulations. And I'm really hand waving at it because, in fact, it's what people talk about a lot. I question how much they understand it. And I know, for example, my boss in Korea and I, at coffee breaks, we used to talk about this a lot because it's just one of those things that it's sometimes a little difficult to wrap your head around. And it has to do, oh yeah, I don't know if I demonstrated this last time, that when we take the Helmholtz coils and the HH coils, and in here we have this really uniform B field. This is pretty interesting. And I sort of talked about it last time. Even if I have that mega powerful magnet and I have north, south, and I have this really uniform B field like this, right? Uh, there's no net translational force. So I put the magnet, and I showed it to you last week. I put the magnet in the middle of this uniform field, and the magnet doesn't go anywhere. It's only when out here, when the magnetic field starts to have a divergence, that if I put the mega powerful magnet here, it would get sucked in. But that's only because there's a gradient now, but they don't call it that. There's a curl, there's a circulation, and it has to do with this concept of currents causing field and such. And the best I really can do now is just convey some of the mysteries of Mother Nature in this. For Physics 2200, it's mostly about torques and magnetic fields and torques, B fields and currents and torques, because this is how we produce electricity and how we produce mechanical power from electricity. Okay, so again, the primary thing last week was that what's the field? How fields go from north to south. Fields are generally caused by moving charge carriers. Even in a magnet itself, a permanent magnet, we talked about 0 point energy, but it's about the spins, the orbital spins and the individual electron spins in a magnet are all lined up. So those do represent current flows, circulation of current around in a circle, circulation, curl, see? And so even a permanent magnet has a current. And then so we talk about the basic field of a current of a field around a wire. And yeah, and then we can take the concepts of that. We have this math here, and I won't go into this very deeply, but at the end of the day, we have this equation. And then we developed our right-hand rules, and I showed you, yeah, there's just more of the same. And then you can bend it into a circle, and then you can see how you still have a B field going around, but the ones in the middle tend to add together. So you have this nice field here. And then it also says we can switch from the right-hand rule for a current in a wire to the right-hand rule for a current in a loop. So in a wire, your thumb is the current and the fingers are the B field. And in a loop, your fingers are the current and the thumb is the B field. So then we might as well then use this to segue into this mu here. The mu is called the magnetic moment. And once again, this is tied in with the reason it's called a moment, because it has to do with circulations. And You may remember from Physics 2100, we have the moment of inertia, which we're going to actually exploit. And it's only called a moment because things can have a variety of rotational axes. So we say, well, what's moment of inertia when it spins this way or if it spins that way. So that's why it's called a magnetic moment. And basically, if you recall, there's a definition of an A vector. This is sort of we sort of call a pseudo vector because we have the unit vector n, and that implies normal to something. So we have the area of this loop, right? So you have a radius. So the area is equal to pi r squared. And so we construct this vector called an A vector, and that just means that we just multiply the unit vector n times the area, and also generally speaking, we always put the n in the very middle. And you may recall this from Gauss's law. And do I have the definition of that? Matt, there's the mu itself. Oh yeah, I remember it, and I'll go back. So mu is just equal to capital N, the number of turns, the number of wire loops, wire turns. B fields are usually, and let's see, the current times the area, right, times N hat. So you'll hear engineers express B fields or a coil of wire and B fields. You'll hear the expression ampere turns. So it has and then I don't know if ampere turns has the area built into it or not. But if you hear ampere turns, it comes from this magnetic moment definition. And the nice thing about mu is that the direction, once you have a current in a loop, mu is determined. The A vector is determined because, as in Gauss's law, the A vector is not determined for an open surface, but it is determined for a closed surface. Or if you learn about Lenz's law, the A vector is arbitrary. You define the A vector for a loop of wire, but does no current in it. But when a wire does when a loop has a current, then then mu and A are uniquely determined. And if that sounds confusing, hopefully we can get to it in doing some review session. Okay, yeah, so this was the concept. You have you line up the compass so it points with the direction of the Earth. You set up a known B field at right angles, and you can then figure out what if you put them at right angles, if the resultant is as 45 degrees, you know that the B field, your known B field, is equal to the thing you're trying to measure, and in this case, it's the Earth. Okay, what we have here. This is just blah blah. No, BZ, yeah. B horizontal. Oh yeah, in this case, there you go. That's right. All right. That's the once you know we're using this equation to tell us because um, um, we're putting it in the center of the coils. In the coil, we're not using a Helmholtz coil actually. In fact, well, I've talked to you about it. We're going to learn more about that with the E over M lab. But if I put my compass in the exact middle, then this equation all boils down to this one here. And so that once we set up the conditions here, then we know that the field in the coil at the center is equal to the horizontal component of the Earth's field. And then you combine that with the measurement of the dip meter, and that gets you the Earth's magnetic field. So, like I said, if we want to save time, does anybody have any questions about what you did in this exercise here and how to determine the Earth's magnetic field with this technique? Does anybody have any questions about it? All right, going well. All right. So the idea now in your logbooks is, remember, this is set up like a high school. It is a high school worksheet. Your job is to write this up as if you were doing it on your desktop. So you say, right, first we set this up, then we set that up, and then write up the analysis and such. That's what Philip is going to be looking for. Something we want to see these graphs, and I went over what these graphs mean, that sort of thing. Okay. All right. So the last thing was to measure the Earth's magnetic field as the function of a period and of the permanent magnet oscillating. And so I think my personal feeling is that the lab manual does a really horrible job of developing this concept of the magnetic moment. And I've already shown you about excuse me, the the I demonstrated last week, I believe. I put the coil of wire in the magnetic field. Does that sound? Yeah, I'm quite certain I did that. Do we remember that? I showed you the magnet and the compass, and I made the magnetic field over to my left here, and there's the coil. And the magnet's off to the side because oh, here's the magnet. I've set up uh, and I apologize. I don't know if you guys have the original lab manual. I just put it up on Canvas. So I got this thing set up to do the last part of the original lab. Uh, but anyways, I'm quite certain that I showed you this coil in the background, and I showed you how I could reverse the current in there, and it would rotate. And I know for sure I showed you the powerful magnet sitting there and how it would rotate. Does that all sound familiar?
Yeah.
Yeah,
Yeah.
right. Okay. So, for you guys, you're going to be required to know how to do problems using this equation here. And um, the notice it's all vectors. In general, they're going to just be something mu and b, and let's see, cross product is sine of theta. Right. So it won't always be. So let's see here. So here's how we develop this. Okay, so let's go over this. So if I take my coil and let's see, I have a current flowing through it, and the magnetic moment of the coil and the B field, the blue is an applied B field, are lined up with everybody. So the angle is equal to 0. And individually, I can take the force on a wire, and each time I can notice that now in this case, notice that's phi. We're calling the angle between mu and b is theta. Theta equals 0. So one by one, if I look at f prime, for example, so we see that the current in f prime is traveling this way. Now, do you guys have these notes here, fields? Let's take a look. I thought so you don't have to be trying to scramble to draw these things. Well, I'm just going to make sure you have it right here and now. Let's just turn these into a PDF, print, full slides per page. So it makes the file smaller for you guys. Landscape, yep. And fit to page. Yeah, so now there's 10 instead of the whatever number of pages there were. Did I click the right button? I did. Okay. Oof, my head is woozy. Oh no, lab sections. There it is. 2200. Magnetic fields. It's more than just a torque on a loop. So this is Phys 2200. 2200 magnetic field lab notes. I'm sorry about this. I normally, if I have a case or have lots of pictures like this pre-made, I generally like to give it to the students beforehand so that they don't have to scramble to try to draw all these diagrams. All right, it's taking its sweet time. I don't know why, but it will. Yeah, lately though, the file shows up in the folder before this little thermometer thing is finished. Oh, there it is. Oh, it's done. Okay. It behaved normally. All right. Oh, there it is. Now it's coming. Oh, it's still 3.4 megabytes. Wow. Okay, there you go. I'll publish that later. I'll give you guys a moment to download it. All right, so we have our formula here. So in this case, we have a B field up, and in this case, the phi in this situation, when theta equals 0, phi is always equal to 90 degrees because the current vector is always in the plane of, in this case, x and y axis. The x-axis, the y-axis, z is up, the B field is that way. So I is always at 90 degrees. So in the case of the f primes, it's going to be I times the length of this segment of the loop, which is the little letter b. And you'll see that they point in opposite directions. And then the f vectors are I, A, B. So they point again in opposite directions. So there's no net torque, there's no net translational force. So F net everywhere, F net is equal to 0. And that's both translational and rotational. So then if we go to the other extreme, where now theta is equal to 90 degrees, now we have to look, and we see that in the case of f prime, So phi prime is equal to 0, but phi is still equal to 90. In fact, it always equals to 90 for this. And so it turns out that the force vectors on little a and little b, little a up here, so these two sides of the two edges of the loop, there's this F vector is always there, and the negative F vectors. So and so now the F primes don't even exist. However, the F's themselves are anti-parallel, meaning they're in two different directions, opposite directions, excuse me. It's important. It's equal opposite. There's still the F net translational is still equal to 0. So that's what I said earlier. There's never a net translational force from a magnetic field. So or at least, give me a minute. Yeah, there's never, to be very precise, F dot some translational motion. So this, of course, could be X, Y, Z when you express it like this, is always equal to 0. Of course, yeah, because you can have a wire will move sideways, but there's no net increase in kinetic energy. And so, well, I have to weaken that, because I can imagine there's a couple of, there are hypothetical problems. So this is for charge carriers. I have to be careful. I have to be careful, because the point is they give you this problem where you have this sliding rail, and that of course will accelerate. So there's no net translational force on a current loop or a charge carrier or a permanent magnet from a uniform field. Okay, so now I haven't said anything too stupid. However, we notice that we have now, because we have a fixed rotational axis, we have a torque, and torque is the force times the distance away from that pivot point. And when we're at 90 degrees like this, when theta equals 90, you see that it's half of that distance, b over 2 times f, and also b over 2 times f, because they, in torque space, they add. You don't worry about these negative and positive signs, and it equals to b times f. And then, of course, the next step is you can turn that into an equation. Let's see. Right. So because it's 0 at 0 and it's maximum at 90, we use the sign, and we go back to this equation. And where is that? Oh, right, here it is, IAB. And you notice that, I missed this. Notice that we have these BIA, B times A is equal to area. So then we have the area times the current times the B field. And in this case, n equals 1, but we add the capital N in because we have to be able to take care of all situations. And this is the definition of our magnetic moment. And then we take into account that we have to deal with various angles. So we say, okay, we remember this R cross F here. And so we end up, R cross F gives us this, the I B times little a times the B with the sine of phi. Since B and A are scalars, we can pull them out, and we know that I is the vector. And so then a B is a vector, and so that's how we get the capital A and the I vector and the sign, and that tells us, why don't we use the cross product? And we throw the n in, so it's general purpose. And again, this is where we started off with, and this is where we came back to mu cross B, the torque. And one of the manifestations of this is that the torque is a max at 90 degrees, and it's equal, and torque is equal to 0, of course, at 0 degrees. But I showed you last week that it's also 0 at 180 degrees, which is something, it's a little head scratching. Something was flashing through my mind. Shit. Oh yeah, I remember now. It's just a sort of FYI, because I think it's something you need to know as 2000. Okay, so we have these terms: stable equilibrium and unstable equilibrium. And equilibrium. And you may remember this from 2100 with the spring. And so a stable equilibrium is characterized, it's called the so-called teacup potential. So if this is potential energy, and this is some sort of displacement, and I'm going to put displacement in quotes because it could also be a rotation. And so if you have a force that equals negative some constant times the displacement, so spring is F equals negative kx. So if I pull on the spring, the force pulls back. And so then we also know that you have, for the spring, you have a mu is equal to 1/2 kx squared. And its minima is at the center here at 0. And so you see it increases whether or not x is positive or negative. So that's a stable equilibrium. So we have this torque, which is a rotation, but it goes as mu times b times the sine of phi. And now this thing, depending for the range of, let's see, for phi, it's zero, right? So when phi is 0 to plus 90 or minus 90, then it'll come back to 0. But in the case of the spring is only, there's only one place where the spring force is 0. So you don't know about unstable equilibrium. So the unstable equilibrium looks like this, the inverted teacup. So then so you have the little marble in the teacup. If you drop the marble, if you put the marble at the edge of the teacup, it goes back and forth until it settles in the bottom. And in the inverted teacup, meaning like tea, the drink, if I displace it a little bit, it just falls off. So and this is in the case where you have 180 phi, and then from you have to be slightly greater than, well, no, it'll keep going. Doesn't matter. So either direction, it's just going to keep going. But the torque is 0 at 180. Trying to remember another unstable equilibrium. Well, it's like being on a unicycle, for example. Yeah, you're trying to stay straight up and down. As soon as you start to tilt, unless you add a compensating force, you fall over. Okay, so right, and this is just a generalization of it, summary of what we went over. And this are notes that I don't remember if I wrote this last week. Oh no, the bar magnet. Okay. So the bar magnet, we do this first. And I just measured it a little while ago. Let's see. In my bar magnet. And I got and I'll show 11.25 inches times 2.54 and centimeters per inch. Calculator. It is pretty interesting that you can get the right answer. 11.25, enter, 2.54 times is 28.6 centimeters. And then let's take a look now. It says here, right. So there's a derivation in your manual, and I'm going to go through this only because you probably need to know this for a lecture. And let's see, where is it? Where is it? That's for second order linear differential equation. Where are you? Oh, there it is. See, it's really stated really poorly. Where is the M is the magnetic dipole. Q is the pole. Yeah, so no one knows about. I don't know why they put that there. It's so dumb. I haven't had a chance to rewrite this lab. And this is with the galvanometer. So I guess they don't do the derivative. Oh, they don't do it till here later on instead of in the beginning. Okay. So the torque, yeah, is I times the second derivative of theta as, yeah, because that's the F equal ma. Right. So this is F equals ma. And I wrote it there, isn't it? Interesting. So this is the restoring force is also equal to the mu times yeah, mu times A. I think I'm going on, I'm a little, yeah, here we go. So this is the magnetic moment of the bar. So this little m substitutes for mu. And so just as we just discussed, that's the restoring force. And it can also be equal to I. Now you should remember that the moment of inertia is the, okay, does everybody understand the idea that mass is the measure of an object's inertia? Has anybody ever said that to you before? That means you're supposed to stop snoring and
You
pay
said
attention.
mass is the product of inertia?
No, mass is the measure. Okay, let me get the sheet down here. Now I know I'm getting my stride here. Give me a minute here. I'm just looking to see. All right, so new slide. So you learned about F equals ma, huh? So you also know that there's the three laws, right? This is the second law. So in the when F net equals 0, we have rest or straight line motion. And the first law is referred to as the law of inertia. So inertia means resistance to change. So we're looking for a change, and we want to accelerate something. So to get that acceleration, we have to exert a force. So you notice that the bigger is m, so as m increases, a decreases. So m, if we have if we want a certain a, we need more force as mass increases. Therefore, mass, it characterizes resistance to change. And quotas erat oh, I forget the last one. QED, thus I prove, thus I demonstrate, really, it's not a proof, that inertia or mass is an object, is the measure, the handle, the number. The mass is the measure of an object's inertia. We tend to think of it as weight, but it's not. Mass is not weight. And this is probably the first time that you've been given a way to wrap your head around it. Mass is an object's resistance to change. That's why in outer space, you can lift a 100-ton rock, but the 100-ton rock can still kill you because it still has inertia and it's still going to squish you, even without gravity. Mass is not weight.
So if you were in space and the 100-ton rock was coming at you at a certain speed, even though you could lift it, it doesn't mean you can necessarily stop it.
Correct. Doesn't necessarily mean your body is solid enough to stop it. It may still turn you into a bloody pancake. That's correct.
Good to know.
Oh yeah. Yeah, you guys hopefully you guys get to face it, right?
I never thought about it like that.
Yeah, no, I see, but it's extremely important that you do think of it that way. Mass is a measure of an object's inertia. I mean, I don't like to disparage my colleagues, but I understand physics. Um, well, again, I don't like ringing my own bell, but I spend a lot of time thinking about these things. I really love physics, and I really seek. If you really, probably this is more interesting to Philip, but my hero Richard Feynman, he has these books called the Feynman lectures, and whenever I'm really confused, I go look at the Feynman lectures. I have a beautiful, I don't know why that's showing up, that control win, huh? I have well thumbed copies behind me on my bookshelf. So we have, oh, that's driving me nuts. What is that? How can I get rid of it? Oh well. So we have in the translational world, we have F equals ma, and in the rotational world, we have torque equals I times yeah, I theta double dot, which is oh, alpha, that's right. So we have theta is the rotational coordinate, omega is rotational speed, and alpha is rotational acceleration. Wow, what is causing? I must have something close to my tablet. Yep. Yeah. Oh, the magnet from the iPad cover. Okay. Get that over here out of the way. So, I is moment of inertia, and usually it's like in our case it's going to be 1/2 ml squared, which is the length of the magnet, and hopefully this stuff sounds familiar. And it's basically that if I have some kind of, and it's easiest to understand with a stick, which the best one is right. I don't want to mess up my setup in the over there. I'm looking for this meter stick that I have, and gosh, I don't see it. What else do I have? Well, I have cardboard tubes, but that would be more make believe. I like having something that's real. So I got this here. Let's see. What's the cameras? Well, you can see me in the Zoom camera. So it's a certain amount of difficulty to do it holding the middle of this piece of pipe, and it's much harder to do it holding the end. And of course, it's extremely simple if I rotate it along the axis of the pipe. So hopefully that's familiar to you from 2100. So the analog of that in also in the magnetic field world, the I is, remember, a moment of the magnetic moment. So you have mu. And so in the case of a bar magnet, the mu is expressed as little m, the bar magnet. It's 1/12 ml squared. So in the physical world, the I of the bar magnet is 1/12 ml squared. So I have a scale. We can measure the mass of the bar, and I can measure the length of the bar. And we then right. So we can get measure ml and period, and we get a quantity called m times bh, right? We can determine I. So you see this equation 14. So write down equation 14 in your, well, first of all, let's see. In your logbooks, you should have, yep. Oh, what was that? Whoa, oh, weird. What in the world? I think it's because I have my drawing tablet and my mouse close together. All right, so we start out with the torque equation here, and come on, why can't I? Oh, maybe it's the style. No, something's wrong. Come on. I don't know why I can't bring PowerPoint to the front. What's going on? I'm definitely going to bring my computer. Whoa. Well, it's something. Do I have another magnet around? Let's see. I'll unplug the tablet. And I must have. Wow. Look at this. Oh, let's see. If I unplug the mouse, and maybe now the trackpad's over here. No, everything is screwy. I must have put a magnet close to something. I don't know what. Crap. Isn't that weird? Look at this. What is going on? It's like we have ghosts, huh? Oh, wait a minute. The other thing would be is if something is resting on a keyboard. No. The tablet is disconnected. Is a button stuck? No. I don't see. I don't know what's going on. Let's see. This keyboard might be. We gotta unplug the keyboard next. That's connected to the back of my computer. That's too far away. I know I'm gonna screw something up if I try leaning over that. What is going on? Can you guys still hear me?
Yeah, we can hear you loud and clear.
Okay, so nothing is. Well, I expect the Zoom to be taking up resources. And okay. All right, so now it seems like it's decided to play nice so far. All right. And, well, okay, not completely, but it's getting there. All right. New slide. So let's give it another try. So we have we have this equation, mu cross B, and we just developed, which is for a loop. This is NIA B sine of the angle for a bar magnet, or for any magnet, for a permanent magnet, is M B sine theta, and M is the magnetic moment of a bar magnet. Generally speaking, we don't know what that number is, and we can't measure it. And we also have torque is equal to I, which is the moment of inertia, and so this is the mechanical moment of inertia. And we have then, if we multiply this by the restoring acceleration, yep, and it's related to the second derivative of the equation for theta, and I believe that they say then that yeah, here it is. We set the two equal to each other, and what happened to the, and then, oh, I see. Then there's a famous cartoon showing these two scientists at a blackboard, and it has an equation, and then this cloud that says, then a miracle occurs. And that's what's happened here. Oh my God. Okay. So I'm going to give you second order linear differential equations for dummies. DiffyQ for dummies. Holy shit. Oh my God, this thing needs to be differential equations. So if I have this second order differential equation here, so this means that I have I times d theta, d squared theta, dt squared plus m bh sine of theta. So that's the basic theta. And then this equals 0. And this is called a homogeneous because it equals to 0. So that means that there's no theta dot term. So theta dot term would be like wind resistance that goes as the velocity squared. So we have, for a conservative force, there's no friction. So there's no velocity squared, velocity term, or theta dot term. And the general solution to this is cosine omega t in a nutshell. And omega is the linear rotational speed. And so we also know that if this is also oscillatory, and so that means that it repeats, right? So then omega equals 2 pi times the frequency, and then we have a thing called a period, which is 1 over f. So having said all that, you see that equation 14 has, yeah, so I even know how to do this. So you end up with something like this. D squared theta dt plus m bh over I sine of theta. And then that means that this here is defined as omega squared equals MBH over I. So these are all the steps they skipped. So omega equals MBH over I square root. And then that equals, so that means that F equals that 1 over 2 pi M BH over I to the 1/2 power. And then if I invert that to get period, then I get the 2 pi square root of I over MBH. All right. So there's your 2-minute introduction to differential equations. They're easy when they're oscillatory and they don't have a whatever coordinate you have. As long as you don't need the first time derivative, you're like, oh, I'm happy. It's like quadratic equation. If you don't have the like when you're doing 1/2 AT squared, and if you don't have the velocity term, then you're really happy. The t term, you just want t. You don't want t. You want t squared, and you don't need the quadratic equation. Okay, so then we have our miracle. We also have now I equals 1/12 ml squared. So if we measure t, if we measure the period t, we get, we can solve, so equals some number, let's call it A. We can get we can solve for MBH, and that's going to be, let's see, t equals 2 pi I over MBH. So we want to square it, and then we can say MBH equals 2 squared pi squared I squared, no I squared over capital T squared. Yeah, so we can measure M and L, we can get I. So we can't separate these two yet. And then we can also, though, we can say that with the bar magnet, we know that we can set this distance z. So setting up the 90-degree thing again, we can say that the B of the bar magnet is equal to the B of the horizontal component of the Earth. But since we using 11, oh, that's like way the hell back here. Right. BZ over M. Blah, blah, blah. I have it written up somewhere else. I'm not going to do that whole derivation here. All we can know is that we can form this ratio. I just want to cut this short so we can get it done, and I'll show you the notes I have. But if we know both of these things, we can do some algebra to get rid of the M. So if you know BH over M, and you know M times BH. There's a way to get rid of the M, and I'll show you. I put the notes for that here. I'm going to leave that for you guys to figure out after we measure the other numbers we need. And I posted it this morning. Here it is, part B notes right here. So the rest of it is here. Okay, but that's up to you guys. All right, so let's get you the numbers you need, and then we'll be done with this part, and you guys, and then we can do some review. So first of all, you need this number Z, and I gave that to you already, the distance, and I'll show it to you. Oops, it doesn't want to switch again. Here we go. And where did I write that down? Holy shit. This is why I use PowerPoint, because my board skills stink. Well, I don't remember where I wrote it down, so I'll just do it again. I have it here in my logbook, thankfully. So I have it as 11.25 inches. So you guys, I think I got 28 point something. And it might still be on my calculator. Yep, 28.6 centimeters. So let's take a look at that. I will use my cell phone, the Droid Cam. So I have, let's see, I'll get rid of this cord. I don't need the cord. I just have a cord plugged into it to keep the phone charged. So if I can get this to hold still enough, you'll see that the compass is at 45 degrees. Oh, it's hard to see. Let's see if I can zoom it in for you without. Whoa, I just about knocked it all over. Come on. And I can unlock this with my fingerprint. It's got a great fingerprint reader, this computer, this phone. I want Droid Cam. Where are you? Here we go. And I finally got my vaccine text. So the two numbers are 40 and 60. So it was a little difficult to get 45 on there. And I have the compass set at centered at 20 inches. And then I've got the, yesterday I almost decided to bolt down the Helmholtz coils. And the center of the magnet is at 31.5 inches. So that means 11.5 inches. And so if you keep an eye on the compass and the magnet, you'll see I can slide the magnet and the compass changes. So I just slid it around till it was the best I could think of at 45 degrees. And so now I've got that measurement. So then the next is to set up the magnet here. And look at that. So we need to measure the period of it. So of course my stopwatch is in my phone. But one thing you hopefully learned in Physics 2100, that the period of the oscillations doesn't depend on the doesn't depend on the amplitude. So we just get it going and we don't have to worry that it's decaying. But we need some kind of timer. It would be fun if we could time it at home, but I've discovered from experience that there's too much lag. So I will have to, let's see, we should be able to just go to the web and find a timer. So we need a stopwatch. Let's see what happens. Ah, look at that. Mama Google comes through. Okay. So we just started it. The period is when, so if I've all the way to the left, I start, and that's one period, right? So let's see if we can get 10 periods and see if I can settle this thing down a little bit. Probably a bad idea to even try. But now I got a nice swing. So ready, set, go. All right. 1. We'll do 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 30 seconds. And what are these? 60? What's that? 60ths? 30? Let's find out. No, hundredths. Okay. 30.6 seconds for 10. 30.6 seconds for 10 periods. All right. 30.6 seconds for 10 periods. So that means you can figure out T then equals. I've given you the Z, and now I have to measure the mass for you. So one of the things you need to answer, and I think it's in the lab manual, why do 10 T's? We'll be looking for that. You're right up. Excuse me. So I got, once again, I've pinched my wife's baking scale. And also, why can we do 10 periods? And I told you why, but you should remember it has to do with the dependence of period on amplitude. Let's see if I can drop my telephone. And there is the scale. But the base is in the way. Here, I'll just bring it out here. Of course, it's reflecting too, but it has this shield. So let's turn it on. Now, hopefully, I didn't test yet whether the magnet's going to affect the reading, but I just would have to put a, oh, that's interesting. So I have this metal bar. Well, it's symmetric, but it's still going to affect the moment of inertia. Interesting question. Well, certainly we need the mass, but I don't want the mass of the clip that held it up in the air. Oh, and I need it to be in grams. Grams. So this thing isn't capable of fractional grams. So that's gonna, all right, 22 grams. 22 grams. Man, and don't forget, you need to turn it into kilograms. All right, where is the notes? All right, M is equal to 22 grams, and the length is, I can just do this with a metric ruler. The length is 8.7 centimeters. L equals 8.7 centimeters. Okay, so you can determine now with everything I've given you, the background, the notes that are in there for relating these quantities here, B over AM and MBH. So calculate the Earth's magnetic field from that. And it'll be here at my house. And I will have to, you can't really compare it to the previous one, can you? So I will, well, look, let's do it right now. I have this toy here. So let's put the, I'll give you the exact measurement. Let's see if we can get this to work. All right. Don't fall, please. I need to see the camera window so I know what I'm setting up here. All right, so I have this USB thing, detector that I can measure the fields. Let's see, that's something I didn't finish preparing. Okay, get this out of the way. Hopefully this doesn't make too big of a noise. Okay, probably scared my dog. So this thing measures all three axes, so it doesn't even matter which orientation it is, because I just want the magnitude. I have it set up because we're going to do this Faraday's Law lab, and this thing here, I set it up, and let's see, I'll show you. Might as well take advantage of all this cameras I got going on here. I wish there was a way for you guys to be able to just pick the cameras and manipulate it on your own. So I have to always keep in mind that you guys don't have the big giant monitor like I do. So in the distance there, you'll see we're going to try, we have these coils in miniature that I'm using now, the big black ones. And the detector isn't on there, but there's a track that we put this detector on, and we're going to use an oscilloscope to measure the strength of the B field. And then I made quick slap together on this guy here, this cardboard, to slide that on the very same place as the detector we use. And so we know exactly what the B field is. And it's pretty cool. I was surprised that we could do a pretty good job, actually, of measuring that way. And this actually, too, I know that this rotational measurement actually gets us a pretty good measurement of the Earth's field, but I have yet to do what we're about to do right now. I'm plugging it now into my computer. And like I said, it measures all X, Y, Z axes. So all I have to do is get the X, Y, Z measurements and just add them quadratically, right? There'll be a resultant vector. And although I do want, so maybe I do care because I want the horizontal component, right? So I want this thing to be, so we'll just get a ballpark figure here because I have to figure out how to extract only the horizontal component. So I'm weighting that down. So I know that there's a little tiny chip on the end of this thing. You can't believe this. If you look at the very pointy end there, away from my fingers, there's this tiny little chip. And that tiny little chip is the magnetic detector. All the rest of it is just there to translate the signal from it into USB. Isn't that something? $25. It's amazing. So, I don't know. Yeah, so now this is just to hold it down so I know that I've got the X, Y, and Z, at least whatever axis is up and down is parallel to the Z vector of the Earth. Okay. And then I need this other software. Now I've measured the field inside of what? Oh yeah, we actually measured the field inside of my demo black coils here, and we did last semester, and we actually were able to use what? Oh, I forget. We'll get to it. I'm really amazed at some of the crude techniques we do. Like this semester and last semester, we measured the acceleration of the Earth using a marble on a frickin' toilet paper tube, and it worked. Connect. There it is. And let's see what we get. So this is kind of lame. I don't, there's no, all I can do is have it give me this running table of numbers. And it seems like it's oscillating. And I can't find any explanation of what these are. Fast, what time is it? Oh, we got time. Yeah, this I believe. So notice one of them is 0 all the time. Isn't that interesting? How could that be? What if I rotate this a little bit? Let's see what happens. Oops. So there's some kind of transient. So I don't get that one. That implies that there's no vertical component to me, just horizontal components. Okay, sorry, I got to play a little bit. I'm going to turn on the big coils. So this will help us determine which is the horizontal and vertical components here. So if I turn this on, now the detector is on, and I'm going to turn so the north is pointed at me. Yep, and now we see, So you notice now I'm getting readings on the x-axis there. So I know, yep, so X and Z represent the horizontal plane, because those ones, I know when I turn on my black coils, so you see my black coils are here, and when I turn on my black coils, I know that the field is going to be along the center of this black coil, and I have this thing pretty much lined up, so it's along that axis. So the X, Y, and Z are relative to that circuit board. So that means that one of these three, the vertical component, won't really be affected by turning on the magnetic field. So I'm going to goose this up to get the strongest possible magnetic field, so there's no ambiguity as to what we're seeing. Okay, so now let's start this again. There's no field. So I don't see any reaction. I don't see anything in the x-axis of the detector. So now I turn that field on, and now we see big change in the x and z coordinates, but not the y coordinate that much. Just a little bit of y coordinate change. Yep. Okay. So that means that the changes a little bit though. So the y-axis is the vertical, and the x and the z-axis represent the horizontal plane. So if I add the x and, no, wait a minute. Yeah, if I add the x and z in quadrature, I'll get the horizontal component. And then the y-axis is my vertical component. I better write this down. So stop this. You guys following me? What I just did? So I have x, y, z of the detector. So I was trying to figure out which one of them is the z-axis, up and down, or the vertical axis, if you will. So I've turned on a magnetic field that I know is only in the horizontal plane. So that means that when I turn it on, the magnetic field, I may see a reaction in all three coordinates, but the two that have the greatest reaction, and that's x and z, those two represent the horizontal plane. And I don't have I have this crude setup over here, but I sat down, I'll say to myself, okay, if I take the values on the x and z axes, so this x and z are horizontal, then I can, those will give me the best measurement of the horizontal component of the Earth's magnetic field. So I'm going to clear this, and I'm going to take some new data. Stop. Now I want to save it. Trouble is, where is it going to say? Yeah, comma delimited. So desktop, Cal State Teaching, lab sections, 2200, magnetic field. So this is 2021 03 25 B field in Dr. H living room. B field of Earth. Okay, save that there. And where are you? Up here. So that is a CSV field. CSV file. While I'm yapping away here, look up, I guess, look up problems you'd like me to do for review. Prepare yourself to tell me, please do problem this or problem that, okay? And these things, unfortunately, oh, I see, it's not exactly a comma delimited. All right, that's no problem. It didn't make a comma, so we want to import from a text file. Comma. What I'm doing is I want to give you a number for the actual Earth's magnetic field, so you can use it to compare to this rotational method. And if I don't get it in the next 5 minutes, I'll work on it and send it to you later. It's just this just is, I don't know, I find all this shit fascinating, and I get an aspect of being a scientist is you get obsessive. And wait till we establish a connection. What the hell does that mean? So what is it? Semicolon. There we go. And it's not working. Oh well. And let's delete this. Yeah, one more time. So let's open this with Word. Can I open it with WordPad? Let's try. Oh, all right. Let's just close that. Don't save. And open with WordPad. And I want to do, I can replace semicolon with a comma. And there it is. And come on. Let's get rid of these things so we don't confuse Excel. Delete, and then let's save it. And now let's try opening it. And nope. And there it is. Great. So milliteslas, huh? We don't need this one. Delete. And why don't we say equals average, and we will, we'll just take the average of all. That's basically 0, huh? And close. Okay, so that's quite small. And that should give us the average of C. All right, so this is the vertical. And these are the two horizontals. Horizontal 1, horizontal 2. And so if I add these in quadrature, so the B horizontal equals the square root, because these are vectors, right? So I have to do Pythagorean theorem, add in quadrature, square root of this one squared plus this one squared. So the horizontal component is millitesla, and there's what 10,000 Gauss in a Tesla. So we have 10 to the fourth Gauss equals 1 Tesla. So a millitesla is 760 millitesla is come on, Harry. 10 to the fourth Gauss per Tesla. And I have now millitesla, so that means that this is equal to this times E minus 3 to get Tesla. What's wrong with that? Name. I don't get it. All right, times 0.001. That's in Tesla. And I multiply that by 10 to the fourth to get Gauss, because I know the Earth's magnetic field is 500 milligauss. Equals this. It's kind of stupid. I should have been able to figure this out directly. So 7.5 Gauss. So it's way strong. Whatever B field we measured there is way stronger. That's okay. Let's see what you guys should do now is calculate the B field, the horizontal component that you got here. And we measured a B horizontal with the detector of 7.6 Gauss, or 0.76 times 10 to the minus 3 Tesla, because you're going to get this T is period, got to be careful, and that's in seconds. So from the Dr. H detector. So let's see what B field you get. So that means that somehow, yeah, I see in the background the uber powerful magnet. So the Earth's magnetic field is so weak that any magnet close by is going to have an effect. All right. Anyways, that's that for the lab. I'll save this and I'll post the rest of these notes at some point. And I'm waiting for this to save, and then I'll make a new one. So does anybody have a problem they'd like me to work? The easiest is something from the textbook. And I won't tell anybody if it's one of your homework problems. Anybody? A problem you want me to do? No? No? Okay, I mean, if you don't, we can just end here if you want. Yes? Go, right? Am I correct? Unless, of course, I think you can still hear me. All right. No one's asking me to work a problem. So I guess, the recording will eventually be there if you need it. The notes that I just wrote up, I'll post them probably tomorrow, because you're supposed to put up a lab day notebook for us to look at. Any other questions? All right. Well, be safe and during spring break. Don't forget the virus is still out there looking to get us, so be careful. And I'll see y'all in 2 weeks, it looks like. And you can ask me questions anytime, even during spring break. Don't worry about that. Okay, going once, going twice. Yes, you're welcome, Moises. Wow, Vicness, you guys telling me how to pronounce that one. Morali, huh? Interesting. I love names. Moises. All right, guys. I'll see you all soon. You're welcome. Take care, guys. All right. See you. All right. Yep, you too, Alex. See you later. Bye, Armando. End.